Hey guys, so welcome to our Monday online lecture on YouTube, and we're starting on Chapter 6. So Chapter 6 concerns energy and equilibrium. A couple of the, shall we say, teasers or appetizers for the chapter. A house painter is rushed into the emergency ward, suffering from a lack of vision after collapsing on the job, and some tins of paint that were taken along on the ambulance ride suggest that methanol, what used to be called methyl alcohol, which is known to be a toxic substance, was part of the paint. The physician starts feeding the patient some ethyl alcohol, what we now call ethanol, from a drip overnight, and the patient makes a complete recovery. You overhear one of the physicians say, "Thank goodness that some reactions are reversible." What do we mean by that? That's something we're going to look at in this chapter. How reactants turning into products can be put into reverse, literally, and turned back into the original reactants. Second scenario, patient in the ER with symptoms of a fever. One of the doctors or nurses plans to give the patient some acetaminophen to try and combat the fever, but the lead physician tells you to stop that. You explain that the patient is suffering from a fever, and the lead doctor says, well, maybe that's a good thing. We'll talk about that and exothermic reactions in the body and why they might be advantageous. So let's begin with just some basic ideas about energy in chemical reactions. Two most basic forms we can think about are what we call potential energy and kinetic energy. Now, kinetic energy we've already talked about because we've talked about this energy of movement as molecules move around, and sometimes even atoms connected in a molecule moving around as these chemical bonds stretch and contract, and the bonds sometimes wave from side to side. That's an expression of kinetic energy. On the other hand, we have potential energy. Like if I take this pen and hold it under tension, there's a potential for something to happen, which is if I let go, that pen's going to go flying off out of my hand. And so that potential, that stored energy, can be turned into kinetic energy. And likewise, kinetic energy can sometimes be turned into potential energy, stored energy. So in a chemical reaction, the molecules with their atoms bonded together show us the change from potential to kinetic and kinetic to potential. Any chemical reaction normally involves breaking bonds and making new bonds. And that breaking of the existing bond or old bond turns the potential energy of the atoms stored in that chemical bond into kinetic energy as the atoms become free and start moving around. But of course, we've also got to make new chemical bonds. So those atoms freed from the bonds will strike other atoms and come together and form new chemical bonds. That turns the kinetic energy back into potential as that chemical bond forms. So we see bonds breaking, turning potential energy into kinetic, and new chemical bonds forming, turning kinetic energy into potential energy. Now, if we look specifically at the breaking of chemical bonds, what we call the bond dissociation energy, that's the energy required for a mole of molecules to break those chemical bonds. A good example would be something like nitrogen gas. The dissociation energy is 226,000 calories per mole. And that's energy that the molecules absorb as they collide with neighboring molecules and break their chemical bonds, giving us these freed atoms which can move about, having turned that potential from the bond into kinetic energy. If we compare that to chlorine, the dissociation energy of chlorine molecules is just 58,000 calories per mole. That's almost a quarter of the energy we saw for nitrogen molecules. So it gives us a couple of ideas that we can express now. The chlorine, taking much less energy, can be described as being more reactive than nitrogen because it takes less effort to break its bond and get a reaction. However, the nitrogen, which takes much more energy to break its bonds, you could describe it as unreactive, but you could also describe it as being stable. It doesn't break its bonds very easily because we have to absorb so much energy, and so we've got relatively stable molecules. So the nitrogen can claim that it's a stable chemical, while the chlorine can claim that it's a reactive chemical because it breaks its bonds so easily compared to the nitrogen, which finds it so hard to break its bonds. So that's one half of the story, breaking the chemical bonds. Of course, we also see new bonds forming. And if we think about nitrogen to nitrogen bonds forming, or chlorine to chlorine, that act of forming the bond causes a release of energy. Those atoms whizzing about with kinetic energy, the bond forms, and it turns that kinetic energy into potential and also heat energy released. And the amount of energy released is exactly the same as the energy being absorbed to break the bonds in the first place. Is what we sometimes call the conservation of energy. Energy is neither created or destroyed, just changed from one form to another. And so this is energy being released. And so from the point of view of these chemicals, we're measuring in this bond formation energy, when the bonds form, we're measuring how much energy the atoms and molecules lose as these chemical bonds form. It's a little bit like a bank balance. When we break bonds, that's an absorption of energy, like your bank account absorbing energy. And so your bank account has a positive balance. If more money goes in, the chemicals have a positive energy balance if they absorb energy from a collision. Meanwhile, if money is taken out of your account continuously, you'll eventually have a negative balance, just like as chemical bonds form and the atoms and molecules lose energy, they have a negative energy balance. They finish with less energy than they started with. So in any chemical reaction, we normally see both processes. Energy being absorbed to break the existing bonds and energy being released to make new chemical bonds. Now, the kind of reaction we see depends on which process was more energy intensive. Was there more energy going in? Or, like this example here, was there more energy coming out? And we can map it atom by atom, bond by bond. For every mole of carbon to hydrogen bonds, that absorbs or needs to absorb 98,000 calories of energy. And with a methane, we've got 1, 2, 3, 4 moles of those bonds to break. With oxygen molecules, it takes 114,000 calories of energy each time to break a mole of these bonds. With 2 moles of oxygen, that's twice the energy. So total energy required to break the existing bonds of 620,000 calories. Compare that to the energy being released as new bonds form. We've got new carbon to oxygen bonds twice over at 192,000 calories per mole at a time. And 1, 2, 3, 4 examples of oxygen to hydrogen bonds breaking. So 112,000 calories per mole, 4 times over. And so the total energy coming back out, released, is 832,000 calories. Every time this reaction occurs, at a molar level. So with more energy coming out, we've got an overall net loss for the reaction of 212,000 calories. Reactions like this, which lose more energy, which means they're giving that energy out, are what we call exothermic reactions. We can recognize them because the energy term for the reaction, what we sometimes call the heat of the reaction, or sometimes call the enthalpy, that's going to be a negative value, like a negative bank balance. You spent more money than you earned. So we see a negative value for the enthalpy of the reaction when it's exothermic. If we included that energy in the equation, that net energy, we'd include it on the right-hand side of the equation because that's where we write the chemicals which come out of the reaction. And that energy is coming out as well. We only show that net difference. We don't normally bother with the total energy in and the total energy out, just that net difference between everything in and out. So there's this much more energy coming out than ever went into the reaction. So of course those reactions giving out energy, if you were holding that reaction in a test tube in your hand and the energy has been given out, then that reaction would feel hot to the touch. So we can show these reactions visually in an energy diagram. We've got the progress of the reaction for the x-axis, and then the energy changes on the y-axis, increasing in energy or decreasing in energy. And so we show that reaction path as if it was a physical barrier in front of us. So if we were standing here and this was our destination, we've got to jump over the barrier, clear that barrier to get to our final destination. We've got to clear that bond breaking energy that has to be absorbed, what we sometimes call the EA, the energy of activation. Put in any amount of energy less than this minimum, and we just hit the wall and slide back down to the beginning, like molecules colliding with each other, but not having enough energy to break the existing bonds, and the molecules just harmlessly bounce off each other. So all the energy in, our bond breaking energy, and all the energy coming back out, our bond making energy. Because the reaction releases more energy than it takes in, of course it's that negative enthalpy value of 212,000 calories. One last thing to point out, we have this transition state, sometimes called the transition point, right at the peak of the curve. This is the imagined moment of collision where bonds are breaking and new bonds are forming. All in that collision, that brief moment in time. And we can draw energy diagrams for pretty much any chemical reaction. Take, for example, nitrogen combining with hydrogen to form ammonia, NH3. Overall, it releases 22,000 calories of energy per mole. So again, we've got the energy of the initial reactants, energy of our final products or destination, and we've got to put all this energy in, which is the bond breaking energy, and is sometimes referred to as the energy of activation. Without this minimum energy requirement, we just come up against the wall, slide back down. We never break the original existing bonds. So all this energy in and this much energy coming out, this much more coming out than ever went in. So from the point of view of the chemicals, they started with this much energy, but they're finishing with just this much. So for their energy balance, they are minus 22,000 calories per mole compared to where they started. Like if you spend more money, a graph of your account over the month would go down. And our transition point right at the top is that imagined moment of collision when bonds are breaking and new bonds are forming. combustion of coal and oxygen to produce carbon dioxide and energy, of course. 93.9 thousand calories of energy per mole. There's a starting point, there's a finish. There's this much energy going in, but this much energy coming out, which is this much more than ever went in. And so compared to where the chemical started in energy, they're finishing lower, finishing minus 93.9 thousand calories of energy. So an exothermic reaction gives out energy, feels hot to the touch. The energy diagram finishes lower than it started. We would show the enthalpy term in the equation on the right-hand side, or that energy term can be quoted as a negative number. So we also have reactions which absorb more energy than they give out. Reactions which absorb more energy are known as endothermic reactions. Good example of that would be the nitrogen gas combusting with oxygen gas. And to make it happen, we need an extra 43,000 calories of energy per mole each time. So the energy term, when we add it to the equation, now is on the left like one of the initial reactants. Because like the nitrogen and oxygen, that 43,000 calories of energy has to be consumed to make the reaction happen. Energy in, but no energy coming back out. We can look at the individual figures for nitrogen to nitrogen bonds or oxygen to oxygen or nitrogen to oxygen, and we see that we do have a surplus on the left-hand side. By the way, as somebody asked me in class today, I would never expect you to have any of these bond dissociation energies or bond formation energies memorized. They'd just be values that you'd be told or that you could work out based on the information that you had at hand. So for reactions which absorb more energy, we see that enthalpy on the left. That enthalpy is also a positive integer because more energy is going in than coming out. And these reactions are the reactions which feel cold to the touch because they're consuming more energy than they produce. They have to take that extra energy from their surroundings, which will feel colder. If we look at an energy diagram for one of these endothermic reactions, it looks similar to what we had for the exothermic. The main difference is that now the products finish higher in energy than we originally started because there's more energy going in, that bond breaking, that energy of activation, and now less energy coming out. Endothermic reactions always have a higher energy for the products and a lower energy for the initial reactants. And an enthalpy, which is positive, because from the chemicals point of view, they started here, but finished this much more higher in energy than when they started. Phosphorus pentachloride is another example of an endothermic reaction. As it breaks down, decomposes into phosphorus trichloride and chlorine gas. 280,000 calories per mole of energy going in. So all this energy in, only this much energy out. So our molecules finish plus 280,000 calories compared to where they started. And of course, our transition state describes that moment of collision when bonds are breaking and new bonds are forming. Okay. That's where we stopped today in class, where we intended to stop. On Wednesday, when we are online for lecture for section 1 at 11 a.m., we'll start with collision theory and rates of reaction. And remember your magic word for the week. Let's see. Magic word for the week will be overthinking it, I'm sure. So be Tyrannosaurus Rex. There you go. That's one my son would know. Magic word, Tyrannosaurus Rex. Okay, that's it. Didn't take long to go through this time, not compared to the lecture. You can always watch this again to take more of it in. And remember, there is a Chem Talk video on energy exchanges like this as well. I'll see everybody soon. Bye.